Have you ever gazed up at the night sky, mesmerized by the endless sea of stars, and wondered what it's all made of? What invisible forces shape the cosmos, and what secrets are hidden in the darkness between the stars? For thousands of years, humans have searched for the rules that govern everything, from the movement of planets to the flicker of distant suns. Our ancestors mapped the heavens, built observatories, and asked questions that still echo today. Just like a video game has code running beneath the surface, our universe has fundamental rules, an invisible script that decides how stars burn, how planets orbit, and how the tiniest particles behave. These rules are the universe's operating system. Understanding these rules isn't just curiosity, it's the foundation of progress. Every scientific breakthrough, every leap forward starts with a question about how the universe works. Discovering gravity let us reach the moon, turning dreams of space travel into reality and opening up the cosmos for exploration. Understanding electromagnetism gave us electricity, lighting up our cities, powering our homes, and connecting the world through the internet. The deeper we go, the more we unlock new medicines that save lives, clean energy that powers the future, and technologies we can't yet imagine, waiting just beyond the horizon. Today, we have incredible tools like the James Webb Space Telescope, peering into the earliest moments of the universe, and the Large Hadron Collider, smashing particles to reveal hidden truths. But even these have limits. The universe's deepest rules are written in the strange, mind-bending language of quantum mechanics, a world where particles can be in two places at once, and reality itself seems to blur. To truly understand these mysteries, we need a new kind of tool, one that doesn't just calculate faster but actually thinks in quantum, mirroring the universe's own logic. Enter quantum computers, machines that don't just process information quickly, but operate on the same bizarre principles as the universe itself, opening doors we never knew existed. Scientists believe these machines could finally unlock the universe's most guarded secrets, revealing answers to questions we've only begun to ask. Google's quantum computing team recently simulated a small piece of the universe's code, a thrilling step toward understanding reality at its most fundamental level. The quest for the universe's rules is entering a bold new era, where curiosity, technology, and imagination combine to push the boundaries of what we know and what we can dream. For most of human history, our tools were simple, just our eyes to observe the world above, and our minds to imagine what lay beyond. We gazed at the night sky, wondering about the mysteries hidden in the stars, searching for meaning in the patterns we saw. Ancient astronomers carefully mapped the stars, connecting dots to form constellations and stories that guided their lives and cultures. They built monuments like Stonehenge, aligning massive stones to track the heavens and mark the passage of time, blending science and spirituality. Early thinkers tried to guess at the universe's makeup, believing everything was made of earth, water, air, and fire. But then, a revolutionary tool changed everything: the telescope. Galileo's discoveries shattered old ideas, revealing a vast, complex cosmos filled with moons, planets, and wonders never before imagined. Newton's laws of gravity gave us a mathematical code for the universe's motion, allowing us to predict the dance of planets and the fall of an apple with the same equations. As our questions deepened, so did our tools. Each new discovery led to even bigger mysteries, pushing us to invent better ways to explore. The 20th century brought Einstein's theory of relativity, which showed us that space and time are woven together and can bend under gravity's pull. And then came the birth of quantum mechanics, a new science that revealed the universe's deepest secrets at the tiniest scales. Scientists discovered that, at the subatomic level, reality is stranger than fiction. Particles can exist in multiple places at once, and become mysteriously linked across vast distances. Particle accelerators revealed a zoo of new particles, each one adding to the complexity of the universe's building blocks. Supercomputers let us simulate the cosmos, modeling galaxies, black holes, and the birth of stars in ways never before possible. But even the mightiest supercomputers struggle with quantum math, quickly reaching their limits as the calculations grow more complex. Simulating just a handful of quantum particles overwhelms classical technology, creating a wall that seems impossible to cross. We've hit a wall, one that only a new kind of computer, built on the rules of quantum physics itself, can break through. That's why quantum computing is the next step in our journey, promising to unlock mysteries that have eluded us for centuries. The search for answers demands a revolution in how we compute, and quantum computers may finally help us solve the puzzles of the universe. What makes a quantum computer so different from the computers we use every day? Why is everyone so excited about this new technology? Let's start with the basics and break it down step by step. Classical computers use bits, ones and zeros, like tiny switches that are either on or off, forming the foundation of all digital technology. Every photo, video, and word you see on your devices is built from long strings of these bits, working together to create everything from simple text to complex graphics. But a bit can only be one thing at a time, either a 1 or a 0, never both. Quantum computers use qubits, which can be 0, 1, or both at once, thanks to a strange property called superposition. This is what gives quantum computers their unique power. Imagine a spinning coin. While it's in the air, it's both heads and tails at the same time, existing in a blend of possibilities. Only when you catch it does it become one or the other, just like measuring a qubit forces it into a definite state. Qubits can also be entangled, linked so that the state of one instantly affects the other, no matter the distance between them, creating a powerful connection. This spooky action at a distance lets quantum computers process information in ways classical computers simply can't, opening up new possibilities for science and technology. 4 classical bits can represent one of 16 combinations at a time. They're limited to a single arrangement in each moment. But 4 qubits can represent all 16 combinations at once, holding multiple possibilities in parallel. Add more qubits, and the power grows exponentially, allowing quantum computers to tackle problems that would take classical computers millions of years. With just 300 qubits, a quantum computer could explore more possibilities than there are atoms in the entire universe, a truly mind-boggling scale. This isn't just about speed, it's a completely new way of thinking, a revolution in how we solve problems and understand the world. Quantum computers are built for complexity, perfectly suited to unraveling the universe's deepest puzzles and mysteries. They're not just faster, they're fundamentally different, opening doors to discoveries we can only begin to imagine. So, what did Google's quantum computer actually do? It simulated the behavior of fundamental particles and the forces between them. Using their Sycamore processor, they modeled a tiny universe governed by a gauge theory, the rules that describe how particles interact. They programmed their qubits to act like a chain of particles, creating a one-dimensional quantum world. The team watched as their simulated particles behaved according to real physics. Particle-antiparticle pairs appeared, separated, and recombined. This was like watching a miniature version of the processes inside an atom's nucleus. It was the largest, most accurate simulation of its kind ever performed on a quantum computer. Running the simulation on up to 41 qubits, they pushed beyond what classical supercomputers can handle. This experiment proved that quantum computers are finally powerful enough to tackle problems in fundamental physics. We're entering an era where we can directly probe the laws of nature. Why can't supercomputers handle these problems? The answer lies in the quantum world's complexity. Quantum mechanics is about probabilities and connections. Each particle has a cloud of possible states. Add more particles and the number of possibilities explodes. To simulate a simple molecule like caffeine, you'd need more memory than there are atoms on Earth. Classical computers use definite ones and zeros, a poor fit for the fuzzy world of quantum particles. It's like trying to paint a masterpiece with only black and white crayons. Classical computers must check every possibility one by one. Quantum computers, using superposition, can explore all possibilities at once. That's why Google's experiment was so important. It solved a problem at the edge of what classical machines can verify. Add just a few more qubits, and the simulation becomes impossible for any classical computer. This is quantum advantage, the point where quantum computers do what classical ones can't. We're standing on that threshold. The old tools have reached their limit. Quantum computing is the way forward. To appreciate Google's achievement, we need to talk about gauge theories, the mathematical frameworks that describe the universe's fundamental forces. The standard model of particle physics is built on these theories, explaining everything from electromagnetism to the strong nuclear force. But solving the equations of gauge theories, especially for the strong force, is incredibly hard. Even supercomputers can only provide rough approximations. Quantum computers offer a new approach. Instead of solving impossible equations, they model the behavior directly. It's like building a model wing and testing it in a wind tunnel rather than calculating every airflow. Google's experiment was a quantum wind tunnel for the laws of physics. For the first time, we can build controllable quantum systems that follow nature's deepest rules. Quantum computing brings mind-bending ideas like the many worlds interpretation. This theory suggests that every quantum event splits the universe into parallel realities. Some argue that quantum computers tap into these parallel universes, performing calculations across them all. Others say this is unnecessary speculation. Quantum mechanics works without invoking the multiverse. Still, the debate highlights how quantum computing challenges our understanding of reality. Are these machines multiverse engines or just exploiting quantum information's richness? Either way, they force us to rethink what's possible. Quantum computing has electrified the scientific world. Physicists, chemists, and engineers see it as a tool to solve problems once thought impossible. Imagine designing new drugs or materials by simulating their quantum interactions. The potential is revolutionary: room temperature superconductors, lossless power grids, and more. But there's caution too. Today's quantum computers are small, noisy, and error-prone. Making them stable and scalable is a huge challenge. Some warn that hype could outpace reality, leading to disappointment if breakthroughs are slow. Building a fault-tolerant quantum computer may take decades. Still, each experiment is a crucial step forward. Excitement and skepticism together keep the field moving and grounded. The promise of quantum computers is staggering. In medicine, they could revolutionize drug discovery by simulating molecules at the quantum level. In materials science, they could create new substances for better batteries, solar cells, and climate solutions. Quantum computers might even help unite quantum mechanics and relativity, bringing us closer to a theory of everything. Even now, the quest to build these machines is driving innovation in engineering and quantum technology. Google's experiment marks a new chapter. We're not just observing the universe, but building tools that speak its language. The road ahead is long, but for the first time we have a path to answer our deepest questions. The future of discovery has never looked brighter.